Okay, good morning, future presidents. Is it the midterm? Is that what's worrying you guys? So please remember, midterm 1 week from today in class. There's a practice midterm up. There's a review session this Saturday. It will be held even if the big storm comes through. So please make the GSI Thomas feel good about showing up early Saturday morning for the review session and come and attend. And it will cover material up through the last lecture. So today's lecture will not be covered on the midterms. So just so you know. So today we are going to be talking about magnetism. Okay, magnetism. So this is going to be a new fundamental force. So we've studied two other fundamental forces so far, the electrostatic force and the gravitational force. And this one is going to be the third one, magnetic force. But we're going to see that it is very closely tied to the electrical forces. Okay, so in fact, most physicists do not consider these to be separate forces. They consider them to be identical. So it's closely tied to electricity. Okay, and I think the magnetic force is familiar to most of us. We are all pretty familiar with compasses and the Earth's magnetic field, refrigerator magnets. Okay? But in the same time, it's also a very mysterious force to most of us. So we'll try to build off some of what you guys already know and come away, hopefully today, with a better understanding of magnetic forces and how they work. So some of the things we already know. We know that there are naturally magnetic materials. Okay? So there are natural magnets which occur in nature, and we found ways to use them. We also know that magnets can attract or repel each other. So if you've ever played with just a simple bar magnet like these, okay, so the bar magnets, we've got two colors on here painted for the two different ends, and we're going to talk about that in a minute. These are the North Pole and the South Poles. And we know from, if you've ever played with these, which I'm sure you have, that they can, magnets will alternately attract or repel each other. Right? And we, of course, are going to be talking about this in much more detail today, but we've all had the experience of playing with magnets at some level. So they will attract or repel, and often, in fact, if you've got a nice smooth surface, which we don't really have here, you know that you can get a magnet that if you put them close together, they will start repelling each other and then follow up by attracting each other, right? So magnets can alternately repel or attract each other, which sounds kind of familiar, similar to electrical force, right? So we'll see where that's coming from and why. Okay? We also know that magnets will attract iron or steel objects. Okay, and sticking to them, so this is why magnets stick to your refrigerator. And here's an iron bar, which I can take that magnet and lift it up with. Okay. So there is a very strong attraction to iron or steel, okay. But there's not a universal attraction to all materials. So we know magnets do not stick to, for example, aluminum. Okay. So there's no sticking there. It doesn't stick to wood particularly well. Okay, there's no sticking on that table. This has got a nice brass edge on it, which is metal. So you might think if it sticks to iron, it should stick to, and steel, it should stick to brass. But there is no attraction there whatsoever. Okay. Weird one. We'll stick to the blackboard. That has nothing to do with the blackboard. These are specially painted with metallic paint on the back side. Okay. So in order to make magnets stick to them. which I learned the hard way this morning. But for most materials, the magnets do not stick, so primarily to iron and steel, right? And to other magnets, of course. So there is a very strong attraction there when we have iron and steel, but not to all materials universally. Okay? And of course, we know that the Earth itself has a giant magnetic field, and this is how compasses work that let us steer north and south. The compass was actually invented by the Chinese. Magnetic material has been known for millennia, and since the ancient Chinese and the ancient Greeks. So it's a force that's been around us, and we've used it for thousands of years, but it still is kind of mysterious in terms of the forces that we deal with every day. So we'll try to understand that a little bit better. Okay, so let's talk about just the simple magnet. Okay, and this is the bar magnet that we are all familiar with. So that's just this magnet there, which I'm going to stick up on the board. Okay, so the simple magnet in nature has some analogies to electrical charges, or electrical charges and electrical forces. Okay, so there is a quantity that we call the magnetic charge, or what we can think of as the magnetic charge, but we use a different name for it. We call it magnetic pole. So magnets do not have charges like electrical charges. They have magnetic poles, except for they're used in very similar ways. So old nomenclature that that kept around. Okay. So magnetic poles, and there are two types of magnetic poles. Which you're familiar with from common usage, which are north and south. Just like we have two types of electrical charges, plus and negative. So remember when we were talking about electrical charges, we said there was calling them positive charges and negative charges was just a convenience mathematically, because it let us take care of the signs of attraction and repulsions. But we could have called them anything, okay? And the key part of electrical charges is that like ones repel each other, and the different charges will attract each other. And we're going to see the same with the magnetic poles. Okay? Like magnetic poles will repel each other, and opposite magnetic poles will attract each other. We just have a different name for them. They are north and south. Okay? So, take that off. Okay, there's something key about magnetic poles, though. Which is that they always appear in pairs. Specifically in opposite pairs. Okay, they always appear in opposite pairs. Okay, and we have a name for that. We call it a dipole. Di just means two, so two poles. So there's two poles together, north and a south, and they always appear together. So for a magnetic dipole, just like this magnet we have there, there's our bar magnet, and there's a north pole and a south pole for that magnet. And this is a magnetic dipole. And we didn't talk about electrical dipoles, but let's talk about it now. We can create an electric dipole by having two opposite charges, just like this, separated by a distance. So the idea is that you've got two charges. These could be, our styrofoam balls or even a proton and electron. But if they're connected by some bond, or in this case, if you're thinking about these as styrofoam balls, then you could actually have a physical rod there. If we have a plus charge and a negative charge that are tied together but separated from each other, this is an electrical dipole. And these will have very similar properties to each other. If you think of a magnetic dipole acting similar to electric dipole, then you can already get some sense of why we've got positive and negative, and why some ends attract and some repel, why the magnet flips when we put another one next to it. Okay? So, magnets always appear in nature, bless you, as dipoles. And in terms of the poles, they're very similar to electric charges, like poles repel, okay, and unlike poles attract. Okay, so let's just draw the picture of that to be explicit. So here is the north and south poles of two magnets that we are putting together. So those are opposite poles. So if we do that on the bench with two magnets, so you see the two colors are telling us the different poles. Unlike poles will attract and stick to each other. Okay, so unlike poles attract, if we do the opposite poles, so if we put two south poles together, two black ends, then I'm having to force them together and they will separate from each other. So it's not just that they don't stick, they are physically pushing each other, and the same with the opposite poles, the north poles. Push. Okay, so let's draw a picture of that. So the the opposite poles will be attracted to each other. North will attract south, and south will attract north, equal and opposite forces. Okay. Whereas if you put two like poles together, north and north, okay, they are pushing away from each other. They're repelling each other, and the same with if we take two south poles and put them together. Okay, so that aspect is very similar to electrical charges if we have opposite or like charges attract. Okay, so that means there's fun things we can do with these. Let's zoom down here on the little tabletop. Okay, so magnet tricks. So these are pretty similar to magnets on your refrigerator, okay, but they have a little hole in them so we can keep them aligned. Okay, you can see they're all sticking together right now in the configuration I have them. So that means that we've got, of the four of these, we've got the norths and souths all lined up in a row, so they're all attracting each other. So if I put them on this pole, right, if I put two on there, then they're in the same order, they're just going to attract, right? But if I flip them so we got the poles go in the opposite direction, then they're all going to levitate each other, right? So they're all repelling each other, okay, and providing a force which is lifting these up off of each other. So this is partly why magnetic forces are a little bit mysterious to us, because we can start making things levitate if we start using them cleverly. So, and it's obviously a strong force. It's overcoming the gravitational force of these objects. So we can do the same thing here. This is just the same type of demo, but with larger magnets. So you can see if I put these together with their poles aligned, they're very strongly attracted to each other. Okay? And if I flip it so that we've got the north and souths lying together, then this thing is just going to levitate there, being pushed up by the magnetic forces between the two objects. Okay, so, very similar to electric charges so far, except for in a couple of aspects. One thing is that these magnets are, remember, if we have electrical charge and we charge something, then it's pretty easy to uncharge it. You just have to touch it, give it a path for current flow, especially to ground. But these pretty much stay magnetized, right? It is possible to demagnetize material. We'll talk about that in a little bit. But for the most part, there's no currents flowing through these. Nothing that's coming off through me to the ground to get rid of the magnetic charges between them. So the magnetic forces remain constant. It's an inherent part of the material. Okay, so there are definitely similarities here with the electrical forces, but there are, or there is, one major difference between the electric charges and magnetic dipoles, okay, which comes from the fact that the magnetic poles always arrive in pairs, always appear in pairs, and let's just write down what this major difference is. Okay, so there's one major difference between magnetic poles and electrical charges. Okay. There are a lot of analogies between them. In some ways, it's easy to understand magnetic poles when you think about electrical charges, but here is the major difference between them. If we have a electrical dipole, okay, so here you can imagine, once again, we've got our styrofoam balls, and we've got them bonded with a stick, and we cut that in half. Okay, we're left with two individual charges. Okay, we've got a positive charge and a negative charge. Okay, and we know what's going to happen. Those are going to attract each other or other charges in the environment, but we're left with individual charges. Okay. The difference with magnetic poles is fundamentally very important. If we do the same thing with a magnetic dipole, so here's a magnetic dipole with a north and south pole, and we cut that in half. Okay. What we're left with, instead of two individual charges, is two smaller magnetic dipoles. Right? These north and south poles never appear in nature alone. If we take a magnetic dipole and we cut it in half, then what we produce are two smaller dipoles, magnetic dipoles. Okay? So we can never get a case where we just have a north dipole by itself or a south dipole by itself. Or if we do, we've never seen it, and that's like major Nobel Prize territory to find a magnetic monopole is what we call them. So, but we don't believe they exist. We've never seen them ever in nature. So magnetic monopoles, that's the name of a single pole by itself, isolated, do not exist. At least as far as we have ever been able to tell. Okay, so we've talked about some of the I would say the empirical aspects of magnetism, that you can create magnets and they have poles, and the like poles will repel and the opposite poles will attract. But we haven't really gotten to the core of what is creating the magnetic force. And what we're going to see here in a second is it's very tightly coupled with the electrical force and electricity. So let's talk a little bit about history. And the discovery of electromagnets. So, the tie between electrical forces and magnetic forces was actually found completely by accident by somebody like me, probably a lot more clever than I am, who was lecturing a class like you. And this was in 1820 by a physicist named Ørsted. And he was giving a lecture where he was talking about electrical currents and materials, very similar to our lecture last time. And he just happened to have a compass with him at the time. And a compass just to tell your direction. I don't know, maybe he was hiking or something. I don't know why he had a compass with him at the time. But the connection between electricity and magnetism had not really been made before. And so this was just by a fluke that this discovery was made. So in 1820, when he was giving a lecture like this, he happened to have a compass around. He was doing a lecture on electrical currents, and he discovered that electrical currents produce magnetic fields. Okay, so what he discovered was that when he had a current flowing through a wire, it would make his compass go crazy and start pointing, which means that it was being subject to a magnetic field. Okay, this is a sort of a modern version of that experiment, which shows it a little bit more carefully set up. I've got two magnets here. Okay, you can see that their poles are aligned, so north on the left, south on the right. And this is just a coil. It's just wire that's wrapped around this coil multiple times. Okay, so I'm going to throw the switch, and it's just going to send current through that wire. And so this is sort of a fancy version of what Ørsted was doing in 1820. But when I do that, okay, remember these are just magnets. They're sitting there, and you can see it flips it, right? So let's see if I go the opposite way. Woo. Cool. I see all the sparks coming out of this. I don't want to touch that. Let's see if I can line this back up. There we go. Okay, so you can see all I'm doing is when I'm closing this switch, I'm closing the circuit, I'm sending a current through this coil, and this thing is spinning, very similar to if we had a magnet here, right, where we had the like poles aligned with these magnets on the sides. Okay? So there is being created a magnetic force in here, and it's flipping this around so that the opposite poles are aligned with each other. Okay, so this thing is getting hot. That's cool. Okay, so you can see that there must be a magnetic field that's being produced in this coil when current is flowing through it. Let's draw a picture of that. This is telling us one thing, though, right up front, which is that there obviously has to be a very deep connection between electrical currents and magnetic fields. Okay, so at a level that was not understood before Ørsted made this discovery. So at this point, a lot of people had studied magnetism, but it was still sort of a mysterious force of nature. Right? So let's just draw a picture of our little battery here, just like last time. We got a positive negative voltage, so there is a wire, and we've got a coil here. This is like our coil of wire there. So when we close the switch, we got a closed circuit, so there's current running through here. So there's current running around the coils in there, and that is effectively producing a magnetic field in here. So that looks just like our bar magnet. So the fact that we have current that's running in this coil, so the current is running in this direction. It's running around in circles, so there's current flowing around, and circular pattern is creating a magnetic, what looks effectively like a magnet, okay, sitting in that coil. So this is an electromagnet. It's a magnet that is produced by running current through a wire, through a coil. Okay, so deeper question. So does this, the fact that we can create a magnet by running current through a wire, basically by having electric currents around, have anything to do with the fact that there are materials like this magnet which are inherently magnetic? They have a magnetic field that is part of them naturally. And the answer to that is yes, absolutely. There is a very deep fundamental connection between the fact that electrical current can produce a magnetic field and that materials themselves can be magnetized or magnetic. Okay, so at the microscopic level, electrons orbiting atoms, or orbiting the nucleus in their atoms, carry electrical currents. Okay, electron spinning around its atom. It is a charge. It is in motion. It is a current. The fact that we have electrons spinning around the atoms means that there is constantly a current flowing around an atom. Okay? Now, for most materials, or most atoms, these currents cancel. Okay, what do we mean by that? So we have electrons that are orbiting in one direction, and for most atoms, every electron that's spinning one direction has another electron that is spinning the opposite direction, if you're thinking of these classically. Okay, so the electrons going in this direction have a current, which is determined by the direction they're flowing. Okay, but the electrons spinning the opposite direction have the opposite current, which are canceling out. So let's draw a picture of that. Okay, so this is for a typical atom. Here is our nucleus. Okay, and here are electrons. So we'll have one electron that's spinning in that direction, and for every electron spinning in that direction, there is another electron spinning in the opposite direction, okay, on average. So for most atoms, there is no net current. Okay. And no net current is the same thing as having no current running through this coil. Okay, so there's no magnet, or no magnetic field is produced. Okay, so that is for most typical materials, but there are some exceptions. Okay, and the exceptions are for materials like iron. Okay. Iron, the way that the electrons are configured in the atom, has a substantial number of electrons on the outside that aren't canceling each other, okay, or a handful of atoms that are not electrons that aren't canceling each other and are orbiting in the same direction. So there are multiple electrons orbiting together in the same direction. Okay, this has to do with the atomic properties of iron, which maybe we'll talk about a little bit more when we come back to quantum stuff. Okay, but this has multiple electrons orbiting in the same direction, which means that it's effectively producing this little microscopic magnetic field, just like the currents running through that coil over there. Okay. So each atom of iron is a little atomic magnet. Right? It has a net current flowing around it, which is producing a net magnetic field. So each little atom of that iron is its own magnet. So magnetic materials are inherently ones where there's just a lot of currents at the atomic level. Okay? The electron shells are configured so that the atoms themselves are each little magnets. Okay, so we start thinking about magnetic materials such as these bar magnets, okay, as deriving from electrical currents at the microscopic level, like this picture, okay, then we can immediately come to two conclusions. Okay? So the first conclusion we can come to is that there are no magnetic monopoles, like we've already said. We understand why we can't produce a single north pole or south pole. If all magnetic fields are just produced by currents flowing, when those currents are flowing, they always produce a north and a south. There's no way to produce just a single pole out of that. Okay? And the other is that the magnetic field itself is really just a manifestation of electrical forces and electrical currents. Okay, there's not something fundamentally different from electricity, which produces magnetism. Magnetism is closely coupled to electricity. You could think of it as being a product of electrical forces, but you can also think of them as being just combined together into one new type of force, which we have a name for. Which is just electromagnetism. This is the name for sort of this uber combination of the electrical forces that we've been studying the last few lectures and the magnetic forces that we're studying today. And since they're so closely coupled at the microscopic level, then we just unite them together and call the whole field electromagnetism. Okay, so let's talk about some magnetic materials like these bars here that I've been playing with this lecture. So, magnetic materials. There are a few exotic types of magnetic materials, but usually when we're thinking about magnetic materials, we're thinking about iron or steel. These are the two most common materials that we can produce magnets out of. Okay. And so now when we're thinking about iron and steel, what we want to be thinking about is a configuration of many microscopic atomic magnets. Okay, this picture that we have over there, so which each one of the atoms of the iron is its own little magnet. Okay. So, on average, okay, if you just take a material, a chunk of iron, then we will have the atoms are usually not aligned. Okay. So for normal iron that has not been magnetized, okay, there's still all these little atomic magnets. Each little atom is a magnet, but they're not aligned. So if you have two little atoms that are sitting next together and you're thinking about them as being two little bar magnets, so imagine each one of these as being a little atomic magnet of iron, and they're sitting next to each other. Then if they've got their poles not aligned so that they're flipped relative to each other, there's net zero magnetic force coming off of those. Okay? Whereas if they're aligned, so if their two poles are aligned next to each other, then they put those together and they're producing effectively a much stronger magnet. Okay? So the difference between steel, which is magnetic, and steel is not, is that steel that's not magnetic is that these little individual atoms are not aligned in the big scale of combining them together. And if it's magnetic, then they've somehow been forced to be aligned with each other. So they're producing a strong magnetic field. So we can see a pretty easy demo of that. Here I've got our two magnets again. Okay, so this is just an iron bar. And you've already seen that I can, this is just marginally strong enough to lift up that iron bar, right? So we've got a single magnet. It's obviously producing some magnetic force. Okay? If I take that and combine it with a neighbor, so here we're thinking about having two of those atoms together, those two magnets side by side. I flip the poles, okay, so they should be canceling out with each other. Okay? And then I try to lift it up. There's nothing, right? These are still attracting each other, okay, but their magnetic poles are canceling each other out, okay? And there's no net force that's being produced on this. So by combining them and flipping them, we've effectively canceled their magnetic fields from each other. Okay? Now if I go back and I align them again, okay, so these don't want to be next to each other, so I'm actually having to force them together. Okay? But their magnetic poles are combined into a stronger magnet, okay, and then I can pick that back up very easily. Okay, so if they are not aligned with each other, they're effectively canceling each other out. There's no magnetic field. Okay. So let's see. Wait, can we have the overhead over here? The overhead projector. Just randomly flipping buttons, I'm sure. There we go. Okay, so here is our model of what iron or steel looks like on the microscopic level. And what we got here are just a bunch of individual little magnets that are all lined up side by side. And these things are free to move. Okay, so you can see that if I shake this a little bit. Okay. So you can see I'm sort of giving them a random direction. Now pay attention to what happens when I stop doing this. Right? So they should all be mixed up and pointing pretty much randomly next to each other. But you see they've aligned, right? So a lot of them have aligned there, producing a net magnetic field along here in one direction. That's actually the best I've ever seen them align. Let me do it again. Usually that's not what happens. Wow, it's my lucky day. I'm producing a really strong magnet here by aligning those all together. So normally what would happen is that some regions will align in one direction, some will align in another. Wow, this is great. You can see at least they're struggling a little bit, okay, with each other. You can see some are aligned and some are not aligned in different directions. Okay, so for normal material, what we'll get is, for steel, these atoms naturally want to align with each other because they are, North Pole to South Pole, because there is a magnetic force there that's flipping them. But it naturally won't do it through the whole material. It'll do little microscopic regions where some are aligned in this direction, and some are aligned in this direction, and some aligned in that direction. And on the whole, they will cancel each other out. Oh, you can see it sort of did that there, right? Where these ones are aligned up and down, and these ones are aligned left and right. Okay? So on average for a region, a big piece of steel or iron, you'll get all these little regions where the magnetic fields there are little magnets created at microscopic level, but on the big scale, they are canceling each other out. Okay, so let's see what happens if I do a couple of experiments with this. First off, I'm going to take another magnet here from the outside. So let's imagine we have our piece of steel here, and it's on the whole unmagnetized. I'm going to take another magnet and bring it in. Okay. You can see that the magnetic field that this magnet I'm bringing in is actually turning these, right? So it's trying to turn them so that their north poles are aligned with the north pole of this magnet. Or sorry, their south poles are aligned with the north pole of this magnet. Okay? So this is how we actually produce man-made magnets, is that we will take steel or iron and we will bring in a very strong magnetic field, okay, and we will literally realign the atoms in the piece of iron or steel in order to be lined up together and produce a large-scale magnet. Okay? And one way of doing that is you introduce a magnetic field, and then you take a hammer and you just whack it. You whack that piece of iron as hard as you can, which sends all the atoms sort of spinning a little bit, and then they all line up with the magnetic field you've introduced. Okay? You can also see from this picture, or this demo, why we can take a magnet and stick it to something that is got steel on it, or something similar to that. Okay? When I take, so imagine this is our piece of steel. On the whole, it is not magnetized. You can see it's aligned in a different pattern there. But if I take this magnet and I bring it up to the edge of it, it's going to flip all of those little atomic magnets in the steel, okay, so that their south poles are aligned with the north pole. And when it flips it, right, it's basically producing a little magnet there on the surface, and that magnet is going to attract the magnet I've already produced because the poles are opposite, right? So bringing this in flips all those little atomic magnets on the surface so that their south poles are basically being attracted to the north pole that I'm bringing in, okay, which means that there is a net magnetic material that's produced there on the surface, okay, which is going to be attracting that magnet. Then when I take the magnet away, for most materials, right, I mean for most steel, like your refrigerator, you usually don't actually magnetize your refrigerator by putting a magnet on it. You take it away and then they're much more influenced by their neighbors than they are by the outer one. And that little magnetic field disappears. Okay? So put it in, you can see they're all getting aligned there, and that would produce a net attraction on this magnet I'm bringing in. And take it away and they all are flipping around to try to get into a configuration with their neighbors. So the magnetic field disappears. Okay? So only if we introduce a really strong magnetic field, okay, like this, and then we do something like hit it or heat it up, something to get those atoms shaking so that they all get aligned together, and then cool it off or take the big magnet away, then we can be left with a net magnetic field in there. So we magnetize the steel or the iron. Okay. Likewise, if you have a magnet like this, so this has been magnetized. Okay. If you have a magnet, sometimes you can demagnetize it just by hitting it. You hit strong enough, you give all those atoms in there enough kinetic energy, and they will flip around, and the magnetic field will disappear. So, or by heating it up strong enough, it gives them enough energy to get out of that sort of global pattern. Okay. Any questions so far? Magnets are fun. You guys should get some fridge magnets and play around. Okay. Okay, so there is another connection between magnetism and electricity, which is the opposite of what we've already seen. So we have seen from Ørsted's experiment in 1820 that an electric current can produce a magnetic field. Well, we also can have an opposite effect. Okay, so we've already seen, let me need that board clear. Let me write that over here. We've already seen by creating an electromagnet that an electric current can create a magnetic field. Okay. By running current through those coils, we're producing a little electromagnetic. It looked like a bar magnet. Okay. So there's another physicist named Faraday, whose name you might have heard, who showed the opposite effect. Okay, what he showed was that a changing magnetic field would produce electrical currents. Okay, electrical currents arise when we have an electric potential energy or an electrical field. Okay? So a changing magnetic field can also produce a electrical current or electrical field. So let me show that real fast. So let's see, Wei, if you can come in so you can see this coil and see the board behind it. Let's see. Wei, are you up there? Wei. Break time, union. Hey, Wei. There we go. Okay, great. So you can see me and the coil. Thanks, Wei. So we've got here, what I've just got here is a current meter. That's okay. As long as you can see the meter, that's fine. So what I've got here on the table is this coil. So it's just a coil. There you go. Perfect. So this is just a coil of wire. And this is a very simple demonstration. It's just wire. That's it. It's not attached to anything other than this meter, which is measuring the charge flowing through it, measuring the current flowing through it. Okay? And you can see that that is at 0. And all I'm going to do is take this magnet and I'm going to stick it in there. Okay? So I've introduced the magnet. And one thing you can see, as long as I'm just holding it here still, it's not doing anything. That current just goes to 0. But as soon as I start moving the magnet, you can see that there is a very large current that's being produced in this coil. Okay? So if I hold it still, there's nothing. Okay? But when I start moving that magnet, okay, I'm inducing actually fairly large currents in this circuit here, in this coil. Okay, I can do it with the other end as well. Okay. So this is telling us something, that the magnetic field is able to produce electrical currents, which is the opposite of what we just saw. Okay. But it's a little more subtle because it's not the magnetic field that's producing it, it's the fact that the magnetic field is changing. And the magnetic field is changing because I'm moving the magnet, you can see, which is moving the current. Okay. So, but this shows that there is that this connection is not one way, it's both ways. That we can have magnetic fields producing currents and electrical currents producing magnetic fields. They are tightly coupled together at the basic level. Okay, so this leads to some fun things you can do. So we just wrote this, so a changing magnetic field can produce electrical currents. But what do we know about electrical currents? Electrical currents can produce magnetic fields. So there is a back and forth here between producing electrical currents and producing magnetic fields. And so let me show some demos of that. So what I've got here is basically a coil of wire. It's got some iron in it, which amplifies the magnetic field. Okay? And what I can do is actually just, if I hit this button on it, it just sends a pulse of current running through there, so it produces a really rapid magnetic field in this coil. So it basically turns this very rapidly into a little bar magnet, or to a very big bar magnet, okay? And then it goes away as soon as I leave that on the button. So it's basically creating a very fast changing magnetic field. So let's imagine what happens if I take something like this. So this is aluminum. Aluminum conducts electricity. It's not a very great conductor, but it will conduct electricity. So if I put this on there, so let's think through the process, what's going to happen. So I'm going to hit this button. It's going to produce a magnetic field. That's a changing magnetic field inside of an electrical circuit. This is basically a closed circuit, which is just like this demo I was doing over here. So this is just an electrical circuit, a coil. So the changing magnetic field is going to produce a current flowing through this, electrical current. That electrical current will produce its own little magnet. Okay. And it turns out that there's a basic law that the magnet that is produced by this having current in it has to oppose the magnet that is producing it. So that means that basically the poles are going to be, we're going to have so if this was a north pole coming up, it's going to be producing a north pole going down, which means that it's going to be repelling it. So let me just hit this switch. I can see what happens. So the fact that we had a changing magnetic field produced a current, which produced the opposite magnet, and then suddenly we had two magnets with their poles attached to each other, so they started repelling each other. Oops. I unplugged it. There we go. Okay, they start repelling each other very quickly. So now we can start playing tricks with this. So the aluminum is not a very good conductor. We have other conductors. Let's see, this is brass. Brass is an okay but not great conductor of electricity. Oh, I wasn't expecting that. Can you pick that up for me? Oh, thank you. So brass is okay, now I know to look up when I hit that button. Okay, so brass is a pretty good conductor, not a great conductor. This is lead. Lead is not a good conductor at all of electricity, so that means even though it's got a changing magnetic field, it's not producing much current, so you can see it doesn't want to go anywhere. Okay. I think this one is copper. So copper we know is wire, right? Copper is a very good conductor of electricity. So, pretty good. At least it popped up. Oh, thanks. We're going to be up and down the next few minutes. Here, let me show you this one real fast. So this is aluminum again. Okay, but if you zoom it up on this, this is not a solid ring. This one has a little section cut out on it. So that little section means that this is not a closed circuit, which means that currents cannot flow through here, right? Currents can't flow through a closed circuit. So when we put that on there, it doesn't do anything because there's no circuit running. There's no closed circuit for currents to flow, even though that is the same material as this. Okay, it's just this one is a closed circuit. Oh, so this has to charge up. That's why I'm hitting it so much. There we go. So the closed circuit can jump. Now, let's see what we can do here. We already saw the brass one went pretty high. So what I've got here is liquid nitrogen. Always means good times. So one thing about conducting materials, which we really didn't discuss last time, is that if you cool them down, they conduct even better. Okay? So I'm going to take this ring and I'm going to put it in liquid nitrogen and let it get cold. So when it gets cold, it becomes an even better conductor, which means that, that currents can flow through it much easier. Okay. So I think that's probably pretty good. Okay, so let's try this again with the cold conductor on there. Oh, that's a little better. I'm going to leave that. I will not pick that up with my hands. Let's try the copper again. This time, let's get it cold. It really should have been much more impressive than that. Okay, I think that's probably pretty good. Okay, so should be a really good conductor right now. Oh. Somebody have 911 on your cell phone in case I lose an eye. Okay, so let's see. That was a little better. Maybe I got the materials backwards. Let's try, just for fun, let's try lead again. This time we'll make it cold. So lead's a really poor conductor, but this might help it a little bit. I'm really just playing with liquid nitrogen right now, so I'm not sure exactly what's going to happen on this one. But when you got it, why not? Okay, so this one's a lead one again. Hey, at least it moved this time, right? So it's conducting electricity better. Let's do one last one. So I'm going to take multiple rings of aluminum here. We're going to cool them down. So aluminum becomes a much better conductor when it's cold. Okay, so let's try that with the multiple rings on there. Oops. Right, so magnets. Magnets are fun. So let's do one more, especially magnets and liquid nitrogen. Always a good time. Okay, so let me turn that off before I hurt myself. And let's do one more demo, which is exactly the same concept, but this is a giant magnet like that one, except for this one is goes back and forth instead of just doing one single pulse. This one is constantly changing north-south, north-south. And if I turn it on, Okay. So this is just an aluminum pole, just like those aluminum rings, but this one's a little bit more stable. So the magnet is basically inducing electrical currents inside this aluminum plate. The aluminum plate is producing the opposite magnet, okay, which is being repelled, but in this case it's balanced the forces of the magnet holding it up and gravity pulling it down. So this is a stable configuration, and you can see I can actually play with that a little bit. It's not going anywhere, okay? This is a levitator. This is the same idea behind magnetically levitated trains and other type of transportation. And so there is a lot of current that's being formed in this right now, but I'm not, it's just running in a circle here, so it's not endangering me at all being here. Okay? But it also means there's a lot of power that is flowing around there. And we can see that by doing this. So this is just water. I'm just going to pour the water down there. And right now things aren't, it's not too hot because these are balanced, because I'm not, oops. I got to do this faster. Let's let this set for just a second. And boop. Is that scary? That's just telling me that it's left on so I don't walk away from it for a long time. Let's see if it will let me do this real fast. Actually, I can feel this bowl is getting hot. Okay, it's getting hot because it's got a lot of electrical current running through it. It's got a resistance, remember? So current running through a resistor dissipates heat or produces heat. Okay. So if I push this down so that I'm forcing the magnetic field in there even more, you can hear it vibrating. But you can also see the steam start on it, right? Boy, I hope that's the water. I probably should have used less water. I use the whole thing. Yeah, this is really hot now. You can hear it there, sloshing around in there. Okay, we produce a lot of heat through the currents. So I've forced a lot of current to flow through there and produce a lot of heat in that pan. Okay, let me turn this off without making a mess. Oh, it's too hot to touch. There we go. Okay, so the magnetic forces. So key here is to remember that a magnetic force can produce electrical current. Electrical currents can produce magnetic forces. This can be important when we're studying electromagnetic waves, where we'll see that light radiation is just this effect happening over and over again at the microscopic level. And let's see. That is actually, oh, I want to make one more point. So before we go, which is this demo. So you can see directly from this demo, which demonstrated how an electrical current produces a magnet, you can see the basics of how motors work. So motors basically take electrical currents, electrical power, and produce mechanical power. And they literally do that by having coils like this, okay, inside magnets. Okay. We run a current through there, produces a magnetic field, spins that, okay, and if I were more coordinated, I'd be able to do this, but you can get it where you're flipping the current back and forth in this coil. You're constantly producing a magnet that has its poles flipping back and forth, so it's constantly being repelled by these neighbors and starts spinning. Okay? So exactly the same effect as we showed here, just happening over and over again, a little bit more dramatically in a motor, taking that electrical energy, okay, electrical currents, and transporting into physically this thing rotating. And this thing rotating means it's doing mechanical work. Okay? If we have gears attached to this, we're literally able to get mechanical work out of this, okay, and produce motion. So very simple concept, but the basics of how motors work, so which we're not going to talk about in any more detail than that. So Okay, so let's see. Next time we're talking about light. So we will pick up there.